Welcome viewers to the second lecture for the online series of lectures for the course of linear algebra. In the last lecture, we discussed the definition and various basic operations involved in the business of matrices, but we did not mention precisely where these entries of the matrices are coming from. The entries of the matrices belong to a certain structured set called field. So today's lecture, we start with the definition of a field. Okay. So we have a given set F, and we list out 9 properties here. Addition is commutative, meaning that x plus y is equal to y plus x for all x, y in the given set F. 2. Addition is associative, meaning that x plus y plus z plus x plus y, and then we add the resulting element to z for all x, y, z in the given set F. Okay. Number 3 is that there is a unique element zero in F such that x plus 0 is equal to x for all x in F. Okay, and it actually tells us that x plus 0 is equal to 0 plus x is equal to x. We did not mention it separately because we already mentioned the commutativity of the addition at first, here as a first property. Okay, the fourth one being to each x in F, there corresponds a unique element minus x in F such that x plus minus x is equal to the 0 element of F. Okay. Number 5. Multiplication is commutative meaning that x times y is equal to y times x for all x, y in F. This is the multiplication operation denoted by dot. Okay. 6. Multiplication is also associative, which means that x dot y dot z is equal to x dot y dot z for all x, y, z in F. The 7th property tells us that there is a unique non-zero element 1 in F such that x dot 1 is equal to x for all x in F. It tells us that x dot n is equal to 1 dot x is equal to x, since multiplication is commutative. Okay, so number 8 is that to each non-zero x in F, there exists a unique element x to the minus 1, also denoted as 1 over x, in F such that x times x inverse is going to be equal to the 1, this element 1. The final property being multiplication distributes over addition. Okay, that is x dot y plus z should be the same as x dot y plus x dot z for all x, y, and z in F. Okay, so these are the 9 properties that F should satisfy, this set should satisfy with respect to two operations, addition and multiplication, between its elements. Okay, so F is a set with the two defined operations plus and dot called addition and multiplication respectively between its elements, and with respect to these two operations F is supposed to satisfy these 9 properties. Okay, and then we say that, and also the thing is that it is not mentioned here explicitly, but it has to be satisfied that if I take two elements x and y in F, then the addition of them should also produce an element in F, and if we are given two elements x and y in F, and their multiplication should also produce an element in F. These two properties are called the closure of addition and the closure of multiplication respectively. Okay. In literature you will find these two properties listed as two separate properties, the closure under addition and the closure under multiplication, but we don't state them separately here in our case. Okay, and there is one thing that we for notational convenience, when writing x multiplied with y, we will drop this dot. Okay, so we'll just write x times y like this. Okay, meaning that there is a dot in between, or when we write xy we mean x is multiplied with y. Okay, good. So if the given set F satisfy these 9 properties with respect to addition and multiplication, then this set F is called a field. Okay. Okay, good. So let me erase everything here. Now we know the definition of a field. Now we give certain examples of a field. The The first one that we mentioned is the set of complex numbers denoted by this bold-faced C. Okay, so this is the set of complex numbers, and this set with respect to standard addition and multiplication between complex numbers becomes a field. Okay, so it is left as an exercise for you. So let me write down the standard addition between two complex numbers. A plus ib added to c plus id is going to be equal to a plus c plus I times b plus d. Okay, and the multiplication of these two complex numbers a plus ib and c plus id is given by ac minus bd plus I times AD plus BC, right? Okay, so with respect to these two two operations, addition and multiplication, you are supposed to check that um, C forms a field. Okay, so you have to check that all the 9 properties listed before are going to be satisfied under these two operations for the set of complex numbers. Okay, so do this. Now we define a subfield of the set of the field of complex numbers. A subfield of the set of complex numbers C is a set F of complex numbers which itself is a field. Is a field under the same usual addition and multiplication of, you know, uh, under the same addition and multiplication that the field of complex numbers is equipped with. Okay, so this itself is a field under the usual operations of addition and multiplication of complex numbers. Okay, right. So but now recall from the 9 properties listed earlier that the 0, which is the additive identity of the field, and 1, the multiplicative identity of the field, they are both in the field. Since we require the subfield of the field of complex number to be a field by its own right, we also require these two distinguished elements of the field to be in the subfield as well, right? So 0 and 1 must be in the subfield. Also, if x and y are in the field, so are x plus y minus x, x times y, and the multiplicative inverse of x, provided x is not equal to 0, of course. They are all in F. Okay, and only then we'll have the 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 subset f of complex numbers to be a field, and then we'll say that the subset f of complex number is a subfield of the field of complex numbers. Okay, an example of such a subfield is the field of real numbers denoted by R. Okay, so this is an example of a subfield of the field of complex numbers. Okay, so first of all, R is a subset of C. Okay, how is it a subset of C? It's the set of all complex numbers where the imaginary parts are identically 0, right? So if you choose all the complex numbers such that B is identically 0, we will get the set of real numbers. So we immediately see that R is a subset of um, the field of complex numbers, and well, it's it's an easy thing to check that R satisfies all the listed 9 properties of a field. Okay. Now I need to give you an example that is not a field. The set of all positive integers. Okay. Say which is the set of these numbers, right? 1, 2, 3, all the way up to infinity, which we write at z plus, right? This is a set of all positive integers. Okay, this is a subset of the field of complex numbers, but it is not a subfield for various reasons. The first being that 0 is not, the additive identity 0 is not here in this set of positive integers. So that's a problem. And given a positive integer n, its additive inverse minus n is not a positive integer. Okay, that's another problem. And also, given a positive integer n in z plus, its multiplicative inverse 1 over is not in z plus. And for these 3 reasons, z sub plus is not a subfield of the field of complex numbers C. Okay, we don't need to show that it fails in these 3 aspects. It's enough to show that one of them fails. Okay, but we check explicitly that 3 of them fails. 3 of them fail, and hence z plus is not a subfield of the field of complex numbers. Okay, similarly, using similar reasoning, one can show that the set of integers, the set of all integers denoted by z, okay, from minus infinity all the way up to minus 3, minus 2, 0, sorry, minus 1, 0, and then plus 1, plus 2, plus 3, all the way up to infinity. This set of integers is not a subfield of C, although it's a subset of C. You see that given an integer n in Z, its multiplicative inverse 1 over n is not in Z. Okay. Okay, I think I need to take those integers which are not plus minus 1, because the multiplicative inverse of plus minus 1 are in the set, because the multiplicative inverse of plus 1 is plus 1, and the multiplicative inverse of minus 1 is minus 1. They are both in the set. So if I choose any integer except for plus minus 1, then its multiplicative inverse is not an integer. That's why Z is not a subfield of the field of complex numbers. Okay. Okay. Now I give an exercise for you. You check that the set of all rational numbers denoted by bold-faced Q is a subfield of the field of complex numbers C. Okay, so you check this. Okay, so another example is the set of all complex numbers, in fact real numbers, of the form x plus y times square root of 2, where both x and y are rational numbers, is a subfield of C. Okay, so such a set is denoted by Q of square root of 2. Okay, in the literature. So it means you are taking all numbers of the form x plus y times square root of 2 such that x, y are in the set of rational numbers. Okay, so check that this set forms a subfield of the field of complex numbers. Exercise: check that Q of square root of 2 is a subfield of the field of complex numbers. Okay. Okay. Now we start discussing systems of linear equations back to fourth topic of linear algebra, systems of linear equations. Okay, so suppose F is a field. Okay, so the problem that concerns us now is to find an n-tuple of scalars. So the scalars are precisely elements from the field F. Okay, so when we are saying that something is a scalar, that means that that object is an element of F. Okay, so we are considering n tuple of scalars, meaning that n tuple of elements from F, something like this. Okay, where each of these xi's belong to F. Okay, and that we denote by x1, x2 all the way up to xn. This n tuple belongs to F to the n. Okay, okay, and we want this n tuple to satisfy the following conditions. This n tuple satisfies the conditions a11x1 plus a12x2 all the way up to a1n xn is equal to y1. This is a linear equation in these unknowns x1, x2 all the way up to xn. Okay, and the second equation in xi's is a21 x1 plus a22 x2 all the way up to a2n xn is equal to y2. Finally, our nth equation reads am1 x1 plus am2 x2 plus all the way up to amn xn is equal to ym. Okay, here these objects y1 to ym and all the ei's, okay, I between 1 and m, you see I is running from 1 to m and j is running between 1 and n. Okay, see this way, 1, 2 all the way up to n. So all these aij's and the yi's are given elements of the field F. Okay, all right, they are all given, and these are unknowns x1, x2 all the way up to xn. This n tuple is a variable n tuple. Okay, so any n tuple of elements of F that satisfies each of these m equations is called a solution of this system of linear equations. Okay, it's a system of linear equations consisting of m linear equations. So if we if we find an n tuple that satisfies all these m constituent linear equations, we say that these n tuple of elements of F is a solution of this system. Okay, and in this, if in this system of linear equations these these terms y i's are all zero, then we give it a special name. It's called a system of homogeneous linear equations, or a homogeneous system of linear equations. Okay, so if all the yi's are zero, the system is called homogeneous. Okay. Good. All right. Now the the term the terminology of linear combinations. Okay. Consider multiplying the m linear equation that we stated earlier, m linear equations so we number that system with 1 of 1 by constants C1, C2 all the way up to Cm respectively, and adding them to form a new linear equation, and adding them to form the following new linear equation. Okay, so the first equation was a11 x1 plus a12 x2 all the way up to a1n xn, right, to be equal to y1. Okay, then I multiply this first linear equation by c1 on both sides. Okay, now the second equation is a21 x1, right, then a22 x2 all the way up to a2n xn, right, and that is equal to y2. I multiply this second equation by c2, as I have mentioned here, on both sides, and add to the first resulting equation, right, this way. And we keep doing this thing until we reach the nth equation, am1 x1 am2 x2 all the way up to amn xn, and that final term is going to be equal to cm times yn, right? So this is what we denote by number by 2. this linear equation, the new linear equation that we have found, by multiplying each of the linear equation of the old system by respective constants and adding them up. Excuse me. So now rearranging the terms here from equation number 2, we can rewrite it as C1A11 plus C2A21 all the way up to CMAM1 multiplied with x1, okay, plus dot 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 dot, then C1A1n plus C2A2n plus all the way up to CMAMN times xn is equal to C1y1 plus C2y2 plus all the way up to CMYM. This is our equation number 3. Equation 3 represents the new linear equation in n unknowns, okay, with these coefficients, okay, and the inhomogeneity term given by C1y1 plus C2y2 plus all the way up to CMYM, okay. Alright, so we had the old system 1 consisting of m linear equations. We took the linear combinations of these constituent m linear equations to form this equation number 3, which is our new linear equation with coefficients these all the way up to this, and the inhomogeneity term C1y1 plus C2y2 plus all the way up to CMYM. And now one immediately sees that if this n tuple of scalars satisfy, if this n tuple of scalars satisfies the old system of linear equations, then this n tuple is also going to satisfy this newly obtained linear equation, right? You can easily check that by looking at 2, because you have obtained 3 from by rearranging terms of equation 2. So because you see that if this n tuple satisfies the old system 1, then this thing is going to be equal to y1, right? So this will be C1y1, the first term. The second term would be C2y2, and the last term on the left, the last summand on the left is going to be CMYM. If you add them up, you will precisely get the right hand side of equation 2. Okay, so which tells us that if this n tuple satisfies the old system of m linear equations given by equation 1, then this n tuple is going to satisfy this newly obtained linear equation given by equation number 3. Okay. Okay, so let me erase everything here. I need space. Now, if we have the following system of linear equations, B11 x1 all the way up to B1n xn is equal to z1, and the kth equation of the system is bk1 x1 plus all the way up to bkn xn is equal to zk. Okay, this is a system, given system of linear equations, which we number by 4, where each linear equation in 4 is a linear combination of the linear equations in 1. Okay, so if you don't recall 1, let me write 1 for your convenience here. That was a11x1 all the way up to a1n xn is equal to y1, and the last one was am1 x1 all the way up to amn mn xn is equal to ym. Okay, so this is the old system of linear equations which we numbered by 1, and here in the current setting, each equation of 4 is a linear combination of these m linear equations of 1. Okay, from the argument that we had earlier proves that if x1 x2 all the way up to xn is an n-tuple of elements of f, that satisfies equation 1 is also going to satisfy each of these k equations of the system 4. Okay, in other words, this n tuple is going to satisfy the whole system given by 4. Okay, so we have shown that if a solution, if we have a solution of the system 1, that is going to solve the system 4. Okay, but the system 4 may have solutions that is not going to solve system 1. Okay, right? But if each equation of number 1 can be written as a linear combination of the k equations of system 4, then a solution, any solution of number 4 is also going to solve the system 1. Okay, so now these considerations lead us to the following theorem. So let me write the theorem. Let me state the theorem. Equivalent systems of linear equations have exactly the same solutions. So I shed some light on what it means by equivalent systems, but I did not define it directly. Let me do it now. Two systems of linear equations are said to be equivalent if each equation in each system can be expressed as a linear combination of the equations in the other system. So let me write those two systems. One is number 4 and the other one is number 1. So the number 1 was a11x1 all the way up to a1n xn is equal to y1, and the last equation of this system was am1 x1 all the way up to amn xn is equal to ym. Okay, so this was the first system numbered by 1, and our equation number 4 was the other system given by b11 x1 all the way up to b1n xn is equal to z1, and the kth equation of the second system was bk1 x1 plus all the way up to b sub kn xn is equal to z sub k. Okay, this was our equation number 4. Okay, so these two systems will be equivalent if each equation of 1 can be written as a linear combination of the k equations in 4. Also, each equation of 4 can be written as a linear combination of the m equations in one. Okay, and then we'll say that these two systems are equivalent. And the theorem tells us that equivalent systems of linear equations have exactly the same solutions. Okay. All right. So this very important result of theorem has been proved. Okay. Now I suggest some exercises for you from the book on linear algebra by Hoffman and Kunz. So here is the list of suggested exercises. Exercises from Hoffman and Kunz, page 5, problem number 2, 3, 4, and 5. Okay, and also try 6. Okay, these are the 5 problems you need to solve. Okay, so I'll end the first segment of the second lecture here. In the second segment, we will start talking about elementary row operations. Thank you for attending the first segment of the second lecture.